Today we want to discuss the use of public domain software for electronic design. So, there are many packages, and the course that we have covered this time does not require all of them, but the CD that we will give to you will contain many programs other than what is required for this course. To give you an example, for example, layout of ICs can be done using Magic, and we will put a copy of the Magic program on this. In addition to that, technical drafting of circuits can be done with a program called Xcircuit, and Xcircuit automatically outputs SPICE input decks. So, it is a nice program which can interface with those things. So, we will make a complete set of these public domain programs. These public domain programs are somewhat active in the sense that there are volunteers who are working all the time to improve them. So, what we will give you is the latest version as of now, but we will also give you a list of URLs which you can check, and if you have good connectivity you can download the later versions as well. But these versions are quite okay, and for student work we ourselves, in spite of having commercial software, very often prefer to use these because students get to understand how the software works rather than as a box thing that you go there and click here and this happens. So, here because the software is available and you have to describe the thing that you are simulating in greater detail, therefore, the understanding is in fact somewhat better. So, what I will do today is to first of all explain a little bit of the way that these programs work, and some of these features are quite common to most public domain software. Okay. So, let us begin with the operating system first, and while Windows versions are available for some of these programs, generally most of these programs run on Linux or some type of Unix. So, if you have a Sun workstation, then these will work on Solaris, but almost all of them have the native operating system on which they are developed as Linux, and therefore it is convenient if you can have Linux installed on some machines. So, we will just first of all discuss something about the Linux installation. So, Linux is an operating system just like most other operating systems. It is inherently multi-user and multitasking. So, for example, most versions of Windows do not isolate one user from the other. It is not very difficult if two people are working on the same computer to have access to each other's files. So, therefore, actually it is a slightly modified single user multitasking system, not truly a multi-user multitasking system. But all versions of Unix are inherently multi-user multitasking system. So, therefore, the layers are such that the operating system provides a series of binaries or series of programs which are useful to the operating system. Then it provides a series of applications which are useful to everyone, and then the user can install applications which are accessible to everyone or to individuals. And we will today see first how the file structure and everything that you have in Unix, which is different from that in Windows, with which I assume that you are all familiar. It is somewhat different in case of Linux, and you need not become experts at Linux in order to use it, and particularly the newer versions of Linux are actually quite user friendly, and had it not been for the bias of having been trained with Windows first, most of the time you will find that almost anything that you can do with Windows is also possible with Linux. Of course, there is newer software comes, there sometimes drivers are not available, there are problems because it is a free software and all the software is developed by volunteers. So, as a result, and sometimes manufacturers refuse to divulge technical data which has to be bought, and if it is developed in public domain, then you can't afford to buy that information. So, there are sometimes things which are lacking, but for all practical purposes almost anything that you may want to do in a lab can be done using a Linux system. I strongly encourage you at least in a lab or two to convert most of your machines to dual boot. So it is possible to dual boot machines so that they have the capability of running both Windows and Linux, and you'll find that there are lots of very good facilities which become available for free of cost on the Linux operating system. So what we are going to do today, what we have done is that we have cleaned out 2 or 3 computers, and we'll divide you into 3 or 4 groups. And while we will do the discussion part here, the part that you have to do is to yourself install Linux from scratch onto 3 or 4 machines. So what we have done is that we have taken off 3-4 machines, wiped the disks clean of anything, and we'll give you CD-ROMs from which Linux can be installed, and we will give you a demo of installation first so that you know what is happening there. Then we'll encourage you to install it yourself. That way, that initial fear of something will go wrong, etc., that will go because you yourself have installed it at some time. Okay. The version that we use here is called Fedora. This is because Fedora is the development version of a commercial port of Linux called the Red Hat Enterprise Linux, EL, and most of the commercial software runs on EL. Earlier, by the way, all the advanced software in the world for VLSI design, all the 98% of supercomputers in the world run Linux. Okay, so if you have to do anything really advanced, then you should become used to some version of Unix. Actually, I should say 98% use Unix, and you should get used to some sort of Unix, because for home computation, playing games, music, etc., maybe Windows is okay, but for professional work in the area of advanced engineering, you eventually will have to do that, and this will become even more so in the future. This is at one extreme. The other extreme is in embedded systems, and about half of embedded systems made in the world also use Linux, though you don't know it, because it is installed underneath. So many of the mobiles that you use and many of the handheld computers and handheld devices, notebooks, etc., that you use are actually running Linux. It is embedded, so you do not interact with it directly. So there is some percentage in yourself learning this operating system and teaching your students and giving them familiarity, because if they go to any big company, then it is certain that all the professional work that they do for VLSI design or electronic design and so on will involve some variant of Unix, if not Linux itself. And for example, we have VLSI design software which costs about 10 lakhs to 20 lakhs per license per year. So it's very expensive software, and all of it runs on Linux. And since that uses the Red Hat version of Enterprise Linux, which is in fact derived from Fedora, so therefore we tend to use Fedora, but there are other versions of Linux which you might prefer, but we have been using Fedora for this. Okay, now that is as far as the introduction to the Linux system is concerned. How many of you are familiar with general computer architecture? Because I want to pitch my talk at a level where it is understandable to everyone, but on the other hand it is not beneath knee level, so that I am explaining things that you already know very well. So Borole, I know he's written a book. So, but apart from that, basic computer architecture, how many people are familiar? Okay, so I will introduce a little bit of tutorial. Okay, some 2-3 people might get bored, but since the majority of you haven't done it before, I think it is just worthwhile, not necessary to learn how to install Linux, but just as a preamble, better to describe it. So have you ever wondered, let's do it interactively. Have you ever wondered how a computer boots, and what do you mean by a computer booting? What happens when a computer boots? See, there is no intelligence inside the computer. There is no program loaded. So one of the problems that the operating system has is how to load the operating system itself before the hardware understands file systems, files, directories and so on. Right? At this time, when the machine is just turned on, It doesn't understand files, it doesn't understand directories, it doesn't understand disk geometries, nothing. So it is like lifting yourself from your own bootstraps. You have to teach it a little and then use that to do more and then use that to do more. This is the bootstrapping process. Okay. Now this depends on hardware, but for the PC type of hardware, the only intelligence which is built in is that the BIOS stores a device whose first sector will be read and executed. Okay. So typically it is the first hard disk, but you can of course control, you can boot from a CD-ROM, you can boot from other devices and so on. So that is set in BIOS. So that is preloaded in the ROM which is there. But otherwise there is absolutely no control. Now one big difference between Unix kind of operating systems and Windows kind of operating systems is that Unix insulates you from the hardware details. For example, in Windows you often have to know the path, whether it is on drive C or drive D, etc. Right? So C and D refer to hardware. Unix traditionally grew up at a place where the user was actually miles away, could be logged in from a remote terminal or wherever. So therefore obviously you don't know what is C, what is D, etc. So therefore the file system is such that the user need not know on which disk what is running. You know only one file system which remains the same, and on which physical devices this file system comes, that is of no concern to the user. Okay, this is a big difference. This has a great advantage, however, I tend to complain a lot about Windows, so I am a little biased, take it with a pinch of salt, but this is a big problem. Suppose you add a new hard disk and all the hard disk labels change, and now all the programs which were working, they were supposed to getting their data from C and D, and suddenly everything is lost. Okay, this never ever happens in Windows. Okay, so how that is managed, that is the first thing that we will learn. We will come to booting, which I started with, but we will come to booting a little later, but this is the first part which is actually relevant to installation. Okay, so Unix has what is called a mountable file system. Okay, that means it has a directory structure and physical devices are attached to different points in this directory structure. Okay, so the physical devices are known to the operating system. For example, to take the example of Windows, that program files are on C need not be known to the user. That is known to the operating system in case of Unix. So you can simply say, I want this. The operating system will look up where this is and go to the appropriate directory. Okay, this is one thing. The other thing is that because of this, it is not necessary to have the same file system for the entire directory structure. You can mount this directory structure with totally separate file styles, and indeed Linux and most versions of Unix can read all the file systems which are used by Windows. So as a result, the Windows files can be directly read by Linux. Okay, and how that happens is the following. The way you define the file system is that it starts from, because it's called a tree, therefore it obviously starts from the root. So this is called root, and the root is designated by a forward slash. Okay, this is the traditional name of this directory, a forward slash. Everything comes under this forward slash.
Can we access the window partition in Linux?
Yeah, no problem. In fact, this hard disk that you have been loading from, this has 3 partitions. One is visible to Windows. So if you put it in a Windows machine, then you will see only one hard disk. You put the same thing in Linux, you will see all 3, the Windows partition and so on, and Windows partition can be routinely read by this. So the Windows partition is actually not a Windows partition, it is a FAT32 or NTFS or whatever partition, and that partition there is a software available and it is accessible in Linux. So now you have this forward slash which is a root. Now any hard disk can be grafted onto this directory structure as I develop it at any point that you want. Okay, and that is called mounting. So you mount a hardware device at a particular point in this directory structure, and the Windows equivalent of that is that the disk C is mounted at this root point. First of all, almost every activity has associated with it 3 directories. These directories are one where the binaries will go, one where the configuration information will go, and one where the libraries will go. Okay, so all the libraries are dynamically loaded. So these libraries are loaded in some directory. Okay, now generally wherever it is grafted, these 3 must go on the same route. Okay, it should not happen that binaries are on one disk and the libraries on the other disk, because then it is possible that the other disk doesn't get mounted. Now you will have binaries which won't find their libraries. So it is traditional therefore to have all these 3 to be put on the same physical device, and that the operating system does, you don't have to worry about. Okay, so now the first part traditionally was called bin. This is where all the binary programs which are associated with the operating system. In order to run the operating systems, there are various binary programs which have to be run. For example, the one which makes sense of the file system, the one which keeps track of the time sharing between users, scheduling, etc., etc. All these are programs which are part of the operating system, and all these programs go into this directory called bin. Okay, now after the systems have become more complicated, a new directory has been added to it, that's called sbin. This is not standard in all operating systems, but most modern systems will have a new directory called sbin. So apart from bin, you have system binaries and system binaries. So these are the directories which contain executable programs, okay, associated with the operating system. Then you have the corresponding libraries which go into a directory called lib. Okay, and all the configuration related things for the operating system goes a file called etc. Okay, and all the boot information, which is why I started with this after starting with boot, goes into a directory called boot. Okay, when the system first boots, at that time it doesn't even know this directory structure, right? So therefore the boot directory has to be specially treated. So these are the basic things to do with the operating system. The next level is, there is a series of applications which come standard with the operating system. Okay, so for example, in case of Windows and many other operating systems, a C compiler has to be bought separately. Various languages have to be bought separately. But in case of Unix, the C compiler comes with the operating system. Okay, so these are not part of the operating system. They are not required for running the operating system. But these are very useful utilities which come with the operating system. Such things typically go in a branch of this tree called user. Okay, so user is essentially another directory just under root. Okay, it is spelled USR. Okay, and this user again has these same subdirectories. So under user, then you have user bin, user lib, user doc, user share. Okay, so the binaries go under user bin. So for example, the editor VI, which is often used, or Emacs or whatever, they will go in user bin. The corresponding libraries will go in user lib, not in this lib. Okay, this lib is different from this lib. So this, notice that they share a common root. So if you use a separate hard disk partition or hard disk for user, then you mount it here. Okay, not here. Because you mount it here, then bin, lib, doc are on the same physical device corresponding to this. Okay, so the editors, the compilers, many of these things which you need, they go here. Okay, so this is operating system and this is system wide utilities. Okay, they come here. Now there may be something which is installation specific. For example, all these VLSI design programs, they cannot be nobody else is interested in it. We are interested, somebody else may be interested in graphics, somebody may be interested in communications programs, somebody may be interested in DSP, right? So you would like to mount it as if they are available to everyone, but this cannot be part of the user system. You don't want to mix it up, okay? So then under user, there is a special directory called local. Okay, I'll try to write large. So under user, there is a directory called local, and normally this directory is kept empty when you install the operating system. And now you mount on user local a new tree. This tree has obviously the same structure. So there is a user local bin, there is a user local lib, there is a user local doc, and so on. Okay? So essentially you have this sort of bifurcation under any tree. It's very scientific. And the point is that there is no problem. This could be a Unix operating system. This particular device could have a fat operating system. This dock could be a Windows partition. It doesn't matter. Okay? It is mounted once and for all at that position, and the user finally refers to it by the path. You don't have to worry whether it is C, whether D, it is NTFS, FAT32, doesn't matter. Okay? As far as you are concerned, there is this constructed tree, various parts are grafted. Now for example, suppose you are doing a CD and you are doing an LS. Now imagine the complications which are there. When you do, which is equivalent to dir in DOS or Windows. Okay? Now when you do DOS here, this has a different kind of directory structure and different way that the data is organized. Assume that this has a FAT32 structure, right? That means there is a file allocation table from which you have to see which sector has what, etc., etc. But all of this is transparent to the user, right? Therefore, associated with each file system that you have, there is a module which gets loaded in this bin directory. Okay? And it already knows that from this point downwards is this, and therefore the data on this disk is to be interpreted in this way. Okay? So that's none of your headaches, the operating system takes care of. Is this first part clear? How the file system is constructed? The next part is that when we load this operating system, we will have to do all of this. Okay? So what we do is that we partition the disk. You need to have some extra space, and generally depends on how much separation you want to bring along, but it is quite common to have a separate partition for the root system and a separate partition for the user system and a separate partition for user local. Okay? There is a special reason for it. Now what happens is that suppose something that happened to me right now, your motherboard suddenly died. Okay? Now you change the motherboard. Now this has nothing to do with the operating system. Okay? You should not be required to reload the operating system or do anything, which will be so for Unix. But if you are using a Windows system, God help you, because as soon as your hardware has changed, the software also needs to change along with it. Okay? How do we get that independence in case of Unix? Is because of this structure. Okay? Because the corresponding drivers will get automatically loaded, the user need not be disturbed, and you can start working as soon as the new motherboard has arrived. Okay. Now we have done enough. One final thing, that apart from this user, there is a home partition. And this is where all the personal data of the users goes. Okay? So for example, under this, then there will be various directories, one per user. So for example, you will find one for Dinesh, one for some student, etc., etc. Okay? And this is where you wake up. For example, when somebody logs in, this is where you find yourself. Okay? So what is naturally visible to you is everything below it. You never get to worry about all this stuff which has been installed earlier. Okay? So your concern is maintaining your directory under this path. Okay? So this is about the file system on Linux. Now let's come back to that question that I had originally raised. How does a system boot? Now when the system boots, even the file system is not there. Okay, so it doesn't have the, forget about all this complicated structure, it doesn't have any intelligence to understand anything. Now the way it happens is that it loads the first sector, which has some 512 bytes or whatever, that's all the program, from the first available hardware device which is pointed to by boot. Okay, so this sector is loaded in memory and run. So this program then has an absolute address of a disk sector. Okay, remember it doesn't know files. So it says that such and such disk sector number 3565. Okay, that is where the rest of the stuff is. So that is called stage 1. So it loads the stage 1 then. That means it tells it the starting part, and this part has to be contiguous number of sectors. Okay, and it calls itself a RAM disk. What it does is that it makes a disk structure inside the RAM. So the RAM starts emulating a disk. Okay, so you will often find a file called initrd. The initrd file is the initialization RAM disk. So when the program just starts, it starts off this RAM disk. Okay, it takes a certain part of the RAM, partitions it as if it was a disk, and starts loading these things into the RAM and starts executing it off the RAM. Now that then first thing it loads is the file system. Okay, so it loads the initial file system, and then once it understands the file, then it reads in this etc. This etc has a file called init tab and a file called fs tab. Okay, now when it is loaded, the first program which runs is called init. That is the initialization program. So the initialization program now starts running, and initialization program then forks out into many programs and starts running for each terminal which is there, because this is a multi-user system. So for each terminal a copy of init starts running. Now what init does is it reads the file system table, fs tab, and it is fs tab which tells it which physical hard drive is mounted at which point. Okay, so this is a human readable file in text which says that please mount partition number 7 of disk 2 at this point in the directory tree. Please mount this disk at this point in the directory tree, and this is its file system type. Accordingly, the file systems will be loaded. So if you have only ext3, then only ext3 will be loaded. But if you are also using some FAT32 file system, then FAT32 programs will also be loaded. So all these are then loaded and then transferred to the hard disk. And then at the end of it, the system deletes this RAM disk, system has initialized and started running. Okay, and then on each of the virtual terminals, a program called login runs. Now login is a program which asks for username, password, etc. And every user then has an initialization thing so that you can set up your own environment the way you want. Okay, so it is called a shell. It is the equivalent of the Windows graphics, for example. So Windows gives you only one choice of that graphics. This is how, so if Windows is there, it is there. Whereas in Unix you have a choice. You can run GNOME or you can run KDE. There are many things which are available and you may choose. So whichever is your shell, then that shell is loaded, and for every user these shells then start running. Okay, your path is set, and it is conventional for every user to put a bin directory here also. Okay, so for example, if you go to my directory, you will find a Dinesh bin, and all the programs which are specific to my use, which I want them to come up without giving the path, those I will put in my bin directory. Okay, so this whole thing is very systematic. Everything is according to a particular plan, and this is a graftable thing. You buy a new hard disk, nothing needs to change. Okay, you just decide at which point in this directory tree this will be loaded. Suppose you get lots more users now, and you need many more users for this. There is no need that this thing should be called home. For a large system, you could have another directory called home 2. And the new hard disk can be loaded at home 2. And half the users can then be loaded here, the other half can go there. Okay? So this is the background of the operating system that we are trying to load. Now the way it is loaded is that first of all you have to create room for all this hard disk stuff. Okay? Second, you have to choose which programs will be included. Okay? Because everything is free, there is a huge amount of choice which is available to you. So depending on what you intend to do, you will load the operating system. So all of this is available on a DVD, and which is where our experiment today will begin. Okay? So we have a hard disk on which there is an empty disk. Okay? If you don't have one in your college, then you run a program which will shrink the current Windows partition. Okay? So particularly if you have Vista, then Microsoft guys don't like this public domain software. So they have on purpose installed it in such a way that it becomes difficult to install Linux, because the basic hardware defines only 4 partitions and they use up all 4, but one of them is a dummy. Okay, so you have to delete that dummy partition and shrink the partition on which the Vista partition is there, and Vista itself has a facility which allows you to shrink the disk. So you will have to shrink that before you start all this. Okay, however here we don't have a problem. We have a hard disk which has lots of empty space. If you don't have, then in your colleges this is what you will have to do. Run the operating system and free up some disk space. There are many programs which are available on XP, on other Windows system, which will allow you to shrink existing partitions because you are not using up all of it. Once you have shrunk them, then you will have user space available. Once you have that, then generally what I would suggest is that you create partition which are, first of all you need to have a root partition, obviously that is where everything starts. You need to have a user partition. I recommend that you have user local also, separate. The reason for this is the following. Suppose the operating system needs to be upgraded. Okay, new operating system has come, you want to upgrade this, new version has come. Now if you write a new operating system, then user will get overwritten, the slash will get overwritten. Okay, on the other hand, user local and home need not be overwritten. So all the programs that you have installed, they will continue to run, no problem. Okay, and all the data in the home, that will still be as accessible, no problem. Okay. The other thing is that in Linux you can have symbolic links. Okay. So what happens is that a file which physically exists elsewhere can be called by a different name in a different path by putting a link. It's somewhat like shortcuts. Okay, but shortcut is somewhat graphics, but the symbolic link will then pretend as if it is that directory, and the file structure is such that it automatically keeps track. So if there are many links to the same file, the file will not be deleted unless all the links have been deleted. Okay, so when you delete only the link, don't delete the file. Okay, so this is the basic file system on which we are going to operate, and the minimum things that you require are these 4 partitions, and this partition is also required. It's called swap. Okay, the system uses virtual memory. If you have a process which uses more memory than there is physically available, then what it does is that the least recently used material is just put onto a hard disk partition, and you start using that memory for something else, and then when you are through, you reload it. Okay, so this temporary storage on hard disk is done by a partition called swap. So these are the 4 minimum partitions that you need. If you can afford, then you can put more. For example, on my machine, I have separate partitions called archive. So all archival data, all the archival things for systems, all the old software. Okay, sometimes what happens is that the new version of software comes, but I don't like the new version of software. I like the older one better. But the new version won't be available from anywhere. So then I can archive it to my archive. New operating system comes, the new version comes, I suffer through it and then immediately overwrite it with the older version. Okay, by getting it from the archive. So I have a partition called archive, and you can have your own partitions for various operations. But typically right now what is important is that the software that we are going to use is going to go in this partition, in this user local partition. Okay, and it is common for new software to be installed in user local bin. Okay, which is what we are going. This finishes our discussion of the file system. Okay, now, yeah.
How much space should we keep for this, all these patches separately?
Typically, root could be 4 GB. See, root will have, if you have only these, it depends on how many other partitions you have. For example, there is a partition, I have not given you all the directories. There is a directory called temp, where the user temporary data is kept. Now, depending on what you are doing, that can grow to large values. So, it depends on what is going on, how many people are going to be using it together. But to give you at least some number of an answer with all this explanatory statement, is that about 8 GB each for user local and root and home. Okay, that should be okay, but much less is also okay. Okay, so give 8 GB to user. For example, just 2 GB to slash might also be okay. And home, depending on how many people there are, what kind of quotas you want to allot. Swap, there is an old belief that it should be twice the size of your RAM. Okay, in reality, there is very little to justify this, but because you have to take an arbitrary decision, it's not a bad decision to take. So just double the amount of memory that you have. Essentially, it depends on how many swapped out processes are there. At a given time, they are saying that there will be no more than 2 swapped out processes for the entire memory. So then you require only twice the size of your memory. Obviously, larger the memory should have a larger swap, right? Because that memory has to go to the swap. But on the other hand, the point is, larger the memory, smaller is the probability that you will need swap. So this twice the size of the memory, this harks back to old days where memories used to be quite small. Okay, so I joined my PhD in the year 1971, and when I joined TIFR, there was a huge celebration in the Tata Institute of Fundamental Research, because the fastest computer in India was at that time in TIFR, and its memory had gone from 16 kilobytes to 32 kilobytes. So those were the days when Unix was still around in those days. So those were the days when people had to have swap, and swap needed to be much larger than this. These days, if you can't afford a swap, that is okay, but for want of a better guideline, just double the amount of memory RAM that you have and create a swap partition. Okay, so when you install, you boot with the CD. That requires BIOS settings. Okay, so you grab the BIOS and change the boot sequence so that you boot from the CD. The CD will ask you various questions. This is an international thing, so whether you speak English, what kind of keyboard you have, etc., etc. And eventually it will put you in this disk editor. So you create these partitions and then format these partitions. Okay, and you tell the installer where do you want these partitions mounted. Okay, so unlike Windows, by the way, there is no limitation. Any partition can be anywhere. It doesn't have to be the first partition to boot from. So it can be anywhere. The operating system is smart enough to figure out. So you tell, for example, the second partition on the hard disk might be this, the third partition might be this. So you say put SDA2 on this, SDA3 on this, or whatever. Okay, so it will ask you in what format do you want it. So for example, suppose you want a partition which will be used both by Windows and by Linux. So then you may want to make it FAT32, which can be read by both. So you may mount that partition called, say, WinBack or some such thing, and now both Windows and Linux will be able to use this. Okay, because Linux can read and write to file systems which follow the Windows partition. The other way around is not possible right now. Okay, all right. Now there is a standard which has emerged for installing software from source. Okay, so let me just go through that now, because you will be installing software from source there. There are various formats in which public domain software is distributed. Okay, we are going to use almost everything from source. We are going to compile it ourselves, but pre-compiled versions are also available, and those are really easy. Okay, so I'll just tell you how to install pre-compiled versions. Pre-compiled versions may or may not be available. Okay, remember, once you compile a program, then it becomes specific to your libraries and so on. So if the libraries change, then you have to change that. Okay. On the other hand, if you yourself compile, then those libraries are automatically linked, whatever you have. However, pre-compiled versions come in various packages. The most popular among them is a RPM package. RPM stands for the Red Hat Package Manager. Okay. And the way to install is very simple. You run a program, you have to become root, you have to be the administrator. And you run the program by saying RPM -U for upgrade, I for install. And this stands for verbose and use headers and whatever name.rpm. That's all you need to do. Now this RPM is actually an archive and it contains all the instructions for installing this program. So the, yeah, so you will receive some file which will have some name.rpm. For example, spice.rpm. Okay, so you will say RPM dash capital U, sorry. U stands for upgrade. Essentially, if you have an older version, then if you use U, then the older version will be automatically deleted. If you say I, then the new version will be installed, but the older version will not be deleted. So it is better to do U. That way you don't have all sorts of versions of the same program accumulating. So you do UVH and then the file name. Okay, this file name can be a path. RPM is actually a very powerful program. This file need not even be local. Okay, so instead of a file name, you can actually give a URL. So it will actually download the file from there and then install from there automatically. Okay, provided you have a good enough net connection. Alright, this is not what we are going to do. Okay, because we want to just understand it right from the beginning. Most source code is shipped in the form of tar files and these are often compressed. And they often have the extension .tar.gz or .tgz. Okay, tar is an old name and it actually comes from tape archive, when all the software used to come on tapes. However, these days of course it uses modern devices, but the name has remained. So tar is essentially a tape archive. It's an archive of files. It's an entire directory tree put on a storage medium. So essentially many files are combined into one file, that is called a tar, tape archive. And if it is compressed, then it is called tar.gz, okay, GNU-zip, and compressed to very often .tgz. Almost all source files are available in this format. Okay, now this is the unified procedure for most public domain software. First, download the .tgz file or copy it from the CD that we will give you. Step 1. Okay. Step 2, take it to or copy it to user local. That is where we are going to put our programs. Okay, and now you untar it, open out this. This is equivalent to unzipping on Windows. Okay, so then you say tar extract, uncompress, be verbose, and the file name is this file, whatever .tgz. Okay, you can read it now. Okay, so tar, X for extract, V for being verbose, give me verbose messages, Z for this GZ, that means it is a compressed file, uncompress it first, and F means what follows is a file name. Okay, if you don't use F, then it will expect a device like a tape or some external device. Okay, so then you have, what it will do is it will create a new directory under user local. Okay. Now you go to that directory. So you cd to that directory. For example, Spice may have created a directory called ng Spice, which says new generation Spice. So you cd ng Spice, or IRSIM, so you will say cd IRSIM. Okay. Now this is the standard way of installing all programs. It comes with 2 or 3 utilities which have to be run one after the other. Okay. First you run configure. Configure is a program which looks for things which are required for running this program. All the libraries are there or not, do you have enough memory, is your version correct, is this program supposed to run on this version, etc., etc. So all this checking is done by the configure program. So the configure script comes with the program inside the tar.gz. So you first run that. Okay. So you run /configure. Okay. The reason why you run this is that there is a user program, there is a operating system program also called configure. You don't want to run that one. You want to run the configure of this distribution. Therefore you say /configure. Okay. Having configured, and if everything goes well, then a make file will be created. Okay. So then you say make. Okay. What make does is it runs the C compiler, whatever utilities have to be run, compiles the program and creates the executable. At this time, this executable is in this directory itself. Okay. If all goes well, then no errors will be reported. Right. Then you run make install. Make install copies the binary to user local bin, copies the library to user local lib, whatever I had explained earlier, that is automatically done by make install. Okay. And finally, optionally, you can do clean. This is optional. Because installation has been done, clean will remove all the extra object files, various things which have been created. Okay. And now you have this program available in user local bin, people will be able to use it. This is true of most modern distributed programs. Some of the older programs don't follow this convention. But most modern programs just install exactly like this, and practically all the programs that we will be installing will follow this. Okay. So finally, what are the problems which may appear? Very often during make or during configure, the program may complain that I need such and such thing and it is not there. Okay. So for example, the C compiler is there, but for graphics it needs, say, TCL or some such thing. It will say such and such stuff is not there. Okay. So then you must install those libraries first. Okay. And generally that is not a big deal. There is in Linux, there is a utility called yum, which is used for updating the system. So you simply say yum install this, that or the other, assuming you are on the network. Okay. And it will automatically go and look for that file, download it, install it, and now this will go through. Okay. Or the other thing, it may say that, oh, there is not enough hard disk available, etc., etc. So then you see how to take care of that. Right. Quick review. You have looked at the file structure, you have looked at the boot structure. Okay. You boot with the CD, reboot, everything happens, all the hardware is, drivers are installed, etc., etc. Create usernames, etc. Now a new operating system is there. Now you use a CD or whatever, the CD I give you, for example, that will have .tgz files. Copy the .tgz files to user local, untar the file, go to the directory, and then do those 3 steps: configure, make install. Okay. In fact, this is what the RPM file is doing. Okay. So the RPM file is told where what is there, and rather than you doing it, the RPM file does it. Okay, so it does its own configure, etc., etc. It has scripts inside which do all of this. But it is better first few times to do it yourself, because you become familiar of what is happening in this system. Okay. Now the programs that we are going to install and we are going to run tomorrow and day after. So tomorrow we have a session on digital simulation, and in that in particular we will, as part of the stated lab, we will run this CPL, okay, this pass gate logic, complementary pass gate logic. So there are many examples, adder, various things that we will run to see get a feel of CPL, okay. And if you get time, or if you want to do it later on your own, then you might want to see examples of this thing that Professor Chandorkar did, okay, logical effort of sizing transistors and so on, seeing how it becomes better on. Okay. So tomorrow is the digital simulation day. Tomorrow in the class we would have done the op-amp design, and day after you will design your own op-amp and characterize it. So day after will be SPICE and analog simulation day. Okay. So this is essentially what we have in store for the lab, right. What we will do is now we will break for tea. If it has come, it must have come. Tea is there? Yeah. Okay. So we will have break for tea now, and then we will go over to the lab. Okay.